All right, and the final talk in the session will be by Jacob. He's a grad student at Duke in actually the EC, Electrical and Computer Engineering department, and his research is related to quantum simulation of conical intersections using trapped ions. And it's conducted with a bunch of co-authors you'll see on the slide in just a sec. Yep.
All right. Hey, everyone. I'm Jacob. As mentioned, I'm a grad student at Duke with Ken Brown and Jungsang Kim. And today I'll be talking about quantum simulation of conical intersections with trapped ions. So I would like to thank the organizers for having me speak here. So Henry just talked a little bit about his simulation of trapped ions. This one's going to be using sort of the native interactions between spins and bosons directly instead of kind of trying to ignore them, which is something that has really been ramping up with trapped ions lately. So Ken also mentioned a little bit yesterday that this is an RC3 challenge, which is about scalability, but this is scalable in a different way in the sense that it's simulating an experiment that we know this stuff is true. We can directly simulate it with our laptops, but we can't really show it in molecules directly. So I guess it makes it interesting in that regard. So to that end, let's talk about the topic of simulating molecules with quantum computers, which is really a natural location to apply quantum computing for a number of reasons. They are naturally large ensembles of small particles where quantization is necessary. They often have an unwieldy number of interactions that require drastic simplification. And they're relevant to everything in our lives, in particular biology, drug development, material design, but a bunch of other things. But they're hard to simulate for classical computers and even for quantum computers, which is why there are often a large number of approximations made, from Born-Oppenheimer approximation, which will be relevant to this one, Hartree-Fock bases, Gaussian wave function bases, cutting off at a finite basis size, and a bunch of other things that I probably don't even know about. And these approximations are going to be made for even fault-tolerant quantum computing algorithms. And even when we do make those approximations, they're often going to be hard to find ground states and simulate arbitrary molecules. So instead, we can go the other direction, which I think a number of you here agree with, to use analog simulators. So forgo the digital approach, use every degree of freedom we have available in our system, and really try to find interesting qualitative evidence of phenomena. So how does one go about doing this in trapped ions? Well, I think all quantum platforms have these qubits, these two-level systems, or maybe d-level systems. They can map to qubits and qubits. We just map those to electronic degrees of freedom. And then a number of platforms, especially trapped ions, have some sort of bosonic degree of freedom, which in this case is sort of the coupled Coulomb interaction that creates these normal modes. And we can really map those directly to nuclear degrees of freedom. And then, depending on the interactions we have between those degrees of freedom in our native system, we can start to think about replicating interesting Hamiltonians. So speaking of interesting Hamiltonians, what is a conical intersection? So conical intersection really requires understanding the Born-Oppenheimer approximation to some extent to know what it is. And that's the idea that we have these vastly different mass scales and speed scales for the nuclei and the electrons. And because of this vast difference, we can actually think of the nuclei as sort of being clamped, and as the interaction with the electrons, the result of their kinetic energy on the electron's energy can really be thought of as sort of a perturbation. And we can separate their wave functions and sort of solve for an electronic wave function based on the position of the nuclei, and then we can start to think about solving the nuclear degrees of freedom based on sort of a set of potential energy surfaces that is created by the electronic energy. And so what that's going to look like is sort of like, I guess you kind of saw it in Lawrence's talk earlier. They had these nice, lines that what you could quantize into these vibronic and rotational degrees of freedom, or rotational numbers, and those all relied on the Born-Oppenheimer approximation to make those. And they really provide like an intuitive way to think of the motion of the molecule, because when this Born-Oppenheimer approximation is valid, you can just really sort of think of it as being, their own particles, the nuclei being their own particles, and you can see like maybe these blue wave functions being the nuclear wave functions, and sort of following the natural, path of the potential energy surfaces that are created. However, if these potential energy surfaces start to intersect for whatever reason, this approximation goes out the window, and you really get these highly entangled nuclear electronic states, and the notion of these potential energy surfaces sort of starts to go out the window. So Born-Oppenheimer approximation really does help if it's valid, and when it breaks down, it makes things difficult. However, that's not really what we're going for actually in the simulation. We're not trying to do a calculation that's difficult for classical computers. We're actually trying to show something interesting, as I mentioned, that people haven't been able to do with real molecular systems. That's involving this notion of geometric phase, which I think a lot of people at least have some understanding of some geometric phases in their system. And I guess in the Born-Oppenheimer approximation, the geometric phase can best be understood from this sort of two-level system idea. So let's just imagine we have a simple Hamiltonian that looks like x times sigma x, y times sigma y. Those are Pauli operators, and you can think of x and y as some classical parameters from now. And they'll have eigenenergies. This system will have eigenenergies that are pretty simple, really just plus or minus the radius going away from the origin, and you do get that conical intersection right at the center, and that the typical evolution of an eigenstate will look something like this, just with the basic time dynamic phase, or time-dependent phase. However, if you give these classical parameters some time evolutions, in particular make it adiabatic, adiabatic in this sense means small or slow with respect to how far away it is from the origin, then you actually get a time-dependent phase, which in this case will be an integral of the energy over time. But you get this other phase that is called the geometric phase. And it's called geometric because it really depends on the path that the wave function, as it follows this instantaneous Hamiltonian, the eigenstates of this instantaneous Hamiltonian over time, it only depends on that path. It doesn't depend on how slow or fast it goes, as long as it's adiabatic. And so it turns out that this geometric phase also has a topological quality to it, at least in this Born-Oppenheimer approximation picture, which gives you something called the Berry phase. And that's the idea that if you cause the wave function to go around the conical intersection, and meet up with its original point on the other side, you get a phase of -1. If it didn't surround the conical intersection, then you'll get a trivial phase of 1. And so and also this gives the idea that also if you could somehow manage to split the wave function into two separate wave functions and have it come around on the other side, they will accumulate equal and opposite phases of plus or minus I, and you can see interesting interference effects. And so this is really what we're going to try to measure. And as I mentioned, it's really hard to measure in molecules because molecules, things happen really fast, on the order of femtoseconds, and things are really noisy. So in trapped ions, things are slow and easy, so to some extent. Another way of looking at this effect is actually a sort of a molecular Aharonov-Bohm effect, where in the Aharonov-Bohm effect, you're really putting an electron beam around a solenoid, and the solenoid, even though it doesn't have any magnetic field on the outside of it, actually imparts this path-dependent phase due to the gauge potential. And actually, these conical intersections actually create a synthetic gauge potential that's kind of interesting. And this effect is actually, it's been predicted since a similar time, since the 1950s. So our specific model is going to just be a little bit more complicated. We're just going to have a particle in an ideal 2D harmonic oscillator. So you do get but you still get the spin-dependent forces on the end there. But now you actually have a little bit more structure to your potential energy surfaces. And before quantizing, you can look at your energies, in particular look at your potential energy and plot that. and you'll get something that looks like this. So you'll see that the surfaces meet up in a conical intersection at the center, and the bottom one will go down and back up, which will be important for sort of creating this ground state space that's easy to do the experiment in, and that we can look at this phase interference effect. But after we quantize with the typical ladder operator substitutions, and we end up with the fully quantized model, which is often called the Jan-Teller model. So it looks something like this. And those are familiar with trapped ions can see that this could be pretty easy to replicate. The orange torus thing right there is just sort of showing where that ground state, degenerate ground state space is going to be. The fact that it's degenerate, at least within this Born-Oppenheimer approximation picture, is important because we can really filter out any of the time-dependent phases and focus purely on the geometric phase. So at Duke, we do trapped ion stuff a lot. We have a lot of trapped ion people there. And this particular system we used for this experiment was called red chamber. So on the left here, you see just a layout of what the red chamber is. It's a room temperature setup. On the right, you sort of see just the system in action. This system was run by two of my coworkers, Ye Wang and Chao Feng at the time, and now is actually run by Ke Sun, who you might have talked to yesterday. And then this system typically traps 4 to 7 ions. So in this particular experiment, it was trapping 5. And I just have a few stats listed here. But I guess just important for the rest of the talk is just that we use this two-beam Raman scheme to create these, to do any sort of gates. Henry talked about it a little bit. We are able to address all the ions with one big global beam, and then pick out 2 of the ions with these smaller individual beams that are only 2 microns wide, and we have control over which specific ions we choose. And with that Raman setup, we can start to create the Hamiltonian. However, so other than the fact that we have a bunch of these trapped ion systems at Duke, what makes trapped ions in particular good for a molecular simulation? And that's that trapped ions are essentially just fake molecules. When you think about it, when left alone in a trap, their electronic degrees of freedom naturally separate from their motional degrees, which is essentially just the Born-Oppenheimer approximation. And when you plug in these counterpropagating Raman beams that I talked about just now, and actually shine them at an ion, you get this sinusoidal term, which actually has this motional dependence in it, and you can controllably couple the spin degrees of freedom with the motional degrees of freedom, and really break the Born-Oppenheimer approximation in a controllable way. So that's what makes it interesting for this particular type of physics experiment or chemistry experiment. So I won't go through this too much. We've talked about it a couple times. We use a terbium-171, and we use 355 nanometer beams for our Raman transitions. The particular tools that we're going to use in this simulation are, after quantizing and making a Lambdicki approximation on the sinusoidal term, we have this red sideband transition, which is sort of just a James-Cummings type interaction, blue sideband transition, which is anti-James Cummings, and putting them both together, you just get a spin-dependent push, or sort of like a quantum Rabi model. And immediately looking at this, you can see that it's just part of the Jan-Teller Hamiltonian that we want to create. And so we can think about at least, so this is putting, as Henry mentioned, 2 tones on a single laser and driving the sort of spin-dependent push. And once you do that, you immediately create this double well potential, assuming you have a little bit of detuning in the system to maintain a quadratic form. And if your ion will just naturally field 2 potential energy surfaces split apart. Now, to create the conical intersection, we just want to do that in another direction, a separate direction, and that'll sort of create this this double well potential circularly created around a point, which will be the conical intersection. So we have all the tools to create this Jan-Teller Hamiltonian, and that really gives us the experimental plan, which is essentially just to start in the harmonic oscillator ground state. So that's just the spatial distribution shown here. And then we're going to start actually in the plus state of the spin, and that's because it's the eigenstate of sigma x, and it's going to naturally follow one of those double weld potentials as you turn on the X coupling of the Ion-Taylor Hamiltonian. And so you'll just see it just gets dragged off to the left right there. And then you just turn on that Y coupling adiabatically, and that will open up those doors around the conical intersection and allow for geometric phase interference. So these are just Q-tip simulations. Just like I mentioned earlier, this is pretty easy to simulate, but we actually want to measure this in a system. So that's always been the tough part. As I mentioned, geometric phase will cause this characteristic gap. That's actually the most important thing we want to measure. We want to see this crescent shape with this characteristic gap. And here's just a little video of sort of it happening. So the problem with measuring this wave function at the end is that even in trapped ions, measuring motion is a little bit difficult. And when I say a little bit difficult, it's actually very difficult. And that's because it's hard to directly measure. You only ever measure the qubit state of an ion. And when you do that, you really shine laser light on it. And if it's in a certain state, it's going to fluoresce. And when it fluoresces, any sort of interesting spatial distribution you had is immediately going to thermalize and be not interesting anymore. So the procedure usually goes that we need to map the motional information to the qubit state, measure it, and then keep remapping it and find more and more information about the motion after a bunch of different trials. In this particular case, we can use the fact that we don't actually need the momentum distribution, so we don't need the full density operator or the full Wigner distribution. We just care about the spatial distribution. And so what we're actually going to do is we're going to try to measure the characteristic function of the spatial distribution. And it turns out if you have an extra ion that's uncoupled to the motion, it's actually pretty easy to do this. You just do another spin-dependent push after the simulation on that extra ion, and then you measure that extra ion, and you actually get this characteristic function, or the characteristic function split into two separate parts, one associated with the sigma z basis and another associated with the sigma y basis. And you can really just, in two separate measurement experiments, put those together and you get the full characteristic function, or just the Fourier transform of the spatial distribution of the ion. And so that's exactly what we did. And as I mentioned, you do need an ion that's uncoupled to the motion in the beginning, because otherwise the ion that we actually did the simulation on is going to be highly entangled, and that previous equation is not going to be applicable at all. So we do use the fact that we actually have many ions in this chain. At the time we had 5, but you only really need 2. And you just need to make sure they couple to the same normal modes of motion, so you can do this simulation on one ion and then measure on the other. And so that's exactly what we did. So this is just the characteristic function. The left you have the sigma z basis, so it's just the cosine part, the even information, and on the right you have the sinusoidal information associated with the sigma y basis. So just a couple things to note about this. I don't expect you to have a lot of intuition necessarily, but just that the even information is symmetric up to experimental error. The odd information is anti-symmetric around a specific dividing line. And naively, you'd think that dividing line would either be horizontal or vertical, depending on which Hamiltonian we exactly chose. But it turns out there is this non-trivial rotation that was happened because of AC Stark shift in our experiment. So you just get roughly like a 45-degree rotation. So if you compare it to classical simulations, obviously these are a little too ideal, but you get the same general structure. And if you compare sort of along that dividing line, or sorry, I guess perpendicular to the dividing line, where in the odd information you have sort of the most relevant bumps and ups and downs, you can compare that to classical simulation and you see good agreement. In particular on the even part on the left. On the right, you do start to see some damping on the highest peaks, and that's just because of motional decoherence and things like that. So experiment wasn't perfect. And then you do take the Fourier transform, and you do get the wave function that we're looking for. Obviously a little bit rougher version of it, but you get all the qualitative features that we're looking for, in the sense that you get sort of this minimal population in the center, and on the right where the intersection actually is, and the right where the geometric phase interference would have prevented the wave function from going all the way around. There is a little bit of negative probabilities in there. That's just due to experimental error and no post-processing of the data. I will say, well, one post-processing thing is that we did rotate the wave function to take into account the AC start shift. And if you do compare to a classical simulation, this classical simulation being different from the previous one in that it actually used the real experimental parameters, you get good qualitative agreement. So yeah, that was sort of the main point of the talk. There was another group at University of Sydney who did very similar work, except they looked at the time dynamics around a geometric phase, or around a conical intersection to show geometric phase. So I highly recommend taking a look at that paper as well. I would like to thank the team. So other than myself, there's Gloria, who really did some of the theory work and experimental work as well. Chao and Ye, as I mentioned, who ran the experimental setup. Ken, who he actually came up with the idea. He's sort of the main PI behind this. And then Jungsen, who is the main experimental PI. I would also like to point out that there's some work from Ka here. So he came out with this recent paper on quantum simulation of spin boson models with structured bath. So in this work, he used a set of different spin-dependent forces with randomized phases to create interesting spectral densities. And he can certainly talk to you more about that at his poster. And with that, thanks.
Questions? Consider that.
Yeah, it's a really interesting extension, yeah. I can't think of a really easy way to do it, but I am looking into it. Mm-hmm. Yeah, I usually think of it as, well, so it's on these flat surfaces doing sort of a circle around. If you have these non-abelian cases, I don't know what added complications that brings. I'm sure a lot. No, we just for the picture. No, it was mostly, we just used a different detuning. So. Yeah, that's a good question. I mean, you just have to have some sort of spin-independent forces available and be able to sort of create an arbitrary potential. So it is a little hard because the specific potential has like a square root of x plus y dependence, which is kind of hard to create without having that spin-dependent part in there. But you could think about doing it, and you can do Q-tip simulations and you can show that it actually does make it all the way around. So. I'm not a chemist. I hear there's some debate about that. From my understanding, this geometric phase is for sure real, but the topological part of it is sort of just, a result of looking at these adiabatic potential energy surfaces. And the Born-Oppenheim approximation has to be very valid, and there could be potential error, but I'm not a chemist, so I don't fully know.